Today's podcast is the introduction to graphing rational functions. Before we can graph a rational function, we need to know its domain, any points of discontinuity, vertical asymptotes, and horizontal or slant asymptotes. The first thing is the domain of a rational function. The domain of the rational function is places where the function exists. Things to look for to determine domain are if there is a variable in the denominator or if there is a radical with an even index. To find the domain of the function, if the variable is in the denominator, what we'll do is set the denominator equal to 0 and solve. The function is not defined where the denominator equals 0. This would create either an asymptote or a point of discontinuity. If a radical is in an equation and it has an even index, then we need to guarantee that the radicand is positive, so it has to be set greater than or equal to 0. Then the function is only defined on those values of x. First, let's talk about points of discontinuity. A point of discontinuity is a place where the graph does not exist. There will be a hole there. It's not an asymptote. The branches of the graph don't approach it. They actually go up to the hole, stop, and then jump over the hole and start up again. When a function has a point of discontinuity, the original equation looks like a rational function, but after you simplify, it may look like some other type of function. In our example, f of x is x squared minus 5x plus 6 over the quantity of x minus 3. The first thing we would do is factor the problem, and the numerator factors to x minus 3 times x minus 2, and then that is over the factor of x minus 3. We cancel out the common factors, and we're left with x minus 2. In this situation, because the x minus 3 will cancel out, that tells me, first off, there's going to be a disruption in the graph, and secondly, because it cancels, it's going to be a hole. How do I find out where the hole is? I set the denominator equal to 0. I solve it. What this is telling me when it says x equals 3 is that my hole is when x is 3. It means my graph does not exist at x equals 3. So my domain is x cannot equal 3, but it can equal anything else. I have a hole at x equals 3, or a point of discontinuity. In the next example, I had x cubed minus 8 over x minus 2. I factored x cubed minus 8 using the pattern for a difference of two cubes and got x minus 2 times the quantity of x plus 2x plus 4 over x minus 2. Again, because of this x minus 2, or variable in the denominator, I knew I was going to have some sort of a disruption in my graph. Because it canceled, I knew my disruption was going to be a hole. I needed to find out where it would be, set the denominator equal to 0. My hole is at x equals 2, and my domain is x cannot equal 2. It means the graph exists everywhere except when x equals 2. This one actually ended up looking like a quadratic function as opposed to the first one, which ended up looking like a linear function. My last example on points of discontinuity is x cubed plus 27 over the quantity of x squared plus 8x plus 15. Again, I factored, this time using the pattern for the sum of two cubes. And when I factored it, I got x plus 3 times the quantity of x squared minus 3x plus 9 over x plus 3 times x plus 5. Now, again, I know I'm going to have some disruptions in my graph because I do have variables in the denominator. In this case, I have two disruptions. Because the x plus 3 cancels, I can tell that when x plus 3 equals 0, I'm going to get a hole. When the x plus 5 does not cancel, it means I will still have a rational function, and rational functions have vertical and or horizontal asymptotes. Therefore, I knew that I was going to have a hole at x equals negative 3 and a vertical asymptote at x equals negative 5. I've talked about a vertical asymptote, but we haven't defined it. A vertical asymptote is a vertical line that a graph will approach, but it will never intersect. It is located where a function is not defined, and the vertical asymptotes help you graph the branches of the function. On your calculators, that's what I call the Etch-a-Sketch effect on the older calculators, where it looks like there's a vertical line in it. To find a vertical asymptote, we start with the exact same process as we did for finding points of discontinuity. You factor, you find the domain, you look for the points of discontinuity, which is where the factors cancel, and then any remaining factors set equal to 0 tell you where you have a vertical asymptote. On this example, you can see that after I factored, the x plus 3 had nothing to cancel with. This meant it was not a point of discontinuity, it was a vertical asymptote, and my domain is going to be x cannot equal negative 3. On my next example, again, there was nothing even to factor on this one, but I did have a variable in the denominator, so I set it equal to 0, solved it, and it told me I would have a vertical asymptote at x equals 4. On my next problem, I had x plus 5 over the quantity of x squared plus 8x plus 15. I factored. In this case, I had two places where there were going to be disruptions in my graph, two places where we had domain problems. My domain is that x cannot equal negative 3 and x cannot equal negative 5. But because the x plus 5 canceled, negative 5 is a point of discontinuity, and negative 3 is the vertical asymptote. So you can actually get graphs of rational functions that will have a hole in them somewhere. The next thing we look for are horizontal asymptotes. And horizontal asymptotes are a little bit different. Horizontal asymptotes are horizontal lines that the graph will approach but not intersect when x is either very large or very small. When x is close to 0, the graphs can actually cross the horizontal asymptote. Now think about this in terms of a dinner party. If you're having a dinner party at your home for 2 people, if an extra person shows up, you may not have enough food. You probably just made exactly enough for the people that you invited. However, if you think you're having a party for 50, that extra person doesn't matter quite so much. Everybody can give up just a little bit and there will still be plenty for that 51st person. That's what happens when you're dealing with these graphs and looking for horizontal asymptotes. When you get out to the very ends, when x is very large or very small, additional parts of the problem really don't change the actual value very much. But if you're very close to 0, when you're picking values close to 0, those additional parts of the problem actually matter quite a bit. And we'll talk about this more when we actually graph rational functions in class. To find horizontal asymptotes, it actually depends on the degree or highest exponent of the numerator and denominator of the function. There are 3 rules. If the degree of the numerator is less than the degree of the denominator, there is a horizontal asymptote and it will automatically be at y equals 0. If the degree of the numerator equals the degree of the denominator, there is also a horizontal asymptote, but you have to divide the lead terms to figure out where it is. Lead terms being those where the highest exponent occurs. If the degree of the numerator is greater than the degree of the denominator, then there won't be a horizontal asymptote, but there is possibly a slant asymptote. So let's take a look at the first few problems here, first few examples, and decide what's going to happen with our problems. The first one, if you look at the degrees, the lead coefficients give you the degrees, and both of those are x to the first power. So our lead, our degree of our numerator, equals our degree of our denominator, and it equals 1. That means I'm going to deal with the second rule, which is when they equal. And when they equal, the way you find the horizontal asymptote is to actually just divide out the lead terms. Our lead terms were x and 2x, and if I divide that out, what I get is y equals x over 2x, which the x's will cancel out, and when you reduce that, you get 1/2. So this particular problem would have a horizontal asymptote at y equals 1/2. Our next problem, if you look at the degrees, again, look at those lead coefficients, you can see that the degree of the numerator is 1 and the degree of the denominator is 2. Well, what that means, as far as we're concerned, is that the degree of the numerator has a lower degree. It's less than the degree of the denominator. This is when you have the automatic horizontal asymptote at y equals 0. We don't have to do any calculating. We just have to know that the degree of the numerator is less than the degree of the denominator. Moving on to our last example, we have a degree of x squared, or our league terms are x squared and x. So the degree of the numerator is 2, the degree of the denominator is 1. What this means is that our degree is higher in the numerator, and when our degree is higher in the numerator, we don't have a horizontal asymptote. All we have in this situation is a possible slant asymptote. Now, a horizontal asymptote is a horizontal line the graph approaches. A slant asymptote is an oblique or slanted line that the graph approaches, and these occur only when the degree of the numerator is exactly 1 higher than the degree of the denominator. If it's x cubed over x, you're not going to get a slant asymptote. If it's x cubed over x squared, there's a possibility of a slant asymptote. The way you find the equation of the slant asymptote is to actually divide the denominator into the numerator. You can use polynomial long division, which most of you aren't very comfortable with, or you can use synthetic division, which you learned about last year in Algebra 2. These are the steps for synthetic division. First, we need to decide what to put on the outside, and to do this, we set the denominator equal to 0, and this is going to be our divisor. So we start with x plus 7 equals 0, and get x equals negative 7. So when we set up our synthetic division, we put a negative 7 on the outside of our division. Now we need to set up the inside of our division, and to do that, we're just going to use the coefficients of each term in the numerator. The coefficient of x squared was 1. The coefficient of negative 5x was negative 5. And the coefficient, or the actual constant term, was 8. Now I'll review the process of synthetic division with you. When you do synthetic division, the first term always comes straight down. From this point, synthetic division is repeated multiplication and addition. You never subtract, you never divide, you always multiply and add. So the first thing we're going to do is we're going to multiply the number on the outside, the divisor, times the number that we brought down below the line. Negative 7 times 1 is negative 7. That goes in the next position above the line. Now that we've done that, we always add down, and negative 5 plus negative 7 is negative 12. The next thing we would do is multiply again. So we always start with the number on the outside. So we're going to multiply the negative 7 times the negative 12. And when you do that, you get a positive 84. And then you add down, and we get 92. The number at the end is the remainder. We ignore the remainder for a slant asymptotes. When you do synthetic division, remember the first position was x squared, the second position was x, and the third position was some constant. When you get the answer, your first term is now x, your second term is now your constant. You drop the exponent by 1. X squared became x to the first. X to the first becomes actually x to the 0, which is just the number 1, so it has no x there. So our answer for our slant asymptote is y equals x minus 12, because we ignore the remainder. That concludes your lesson on asymptotes.